Yes, hello guys. Let's start with the lesson 6, Laurent's theorem. In this video, I'm going to introduce some definitions and remarks which are very helpful in UGC NET exams and the concepts which are helpful in solving the objective type questions and the other NET exams. So here we introduce a definition for the pole, singularity, the principal part of Laurent's expansion for Fz, and the residue. So let's go for it. The first definition is on pole. If Fz is analytic in a deleted neighborhood of Z0 and a positive integer n can be found such that. Now, what do you mean by deleted neighborhood of Z0? Suppose this is a point Z0 and let this be a neighborhood of Z0. So I will include all the points of this neighborhood except this point. This is not included in the deleted neighborhood of Z0. Right? So all the points of the neighborhood of Z0 except the point Z0 itself is deleted neighborhood of Z0, right? So the definition says, the definition for the pole says that if Fz is analytic in a deleted neighborhood of Z0 and a positive integer n can be found such that limit z tends to Z0, z minus Z0 the power n Fz is equal to a, where a is this limit, and if this limit is not equal to 0 or infinity, right, then Fz is said to have a pole of order n at Z0. Now when you put n equal to 1, we say the pole is said to be a simple pole, right? Next. Then is a definition for the isolated singularity. A single valued function is said to have singularity at point Z0 if the function is not analytic at Z0. That is singularity of Fz. Furthermore, if the function is analytic in some deleted neighborhood of the point Z0, then the singularity is said to be isolated singularity. Is it clear? For example, Fz is equal to 1 over z. This has isolated singularity at the origin. You put denominator equal to 0 and what you will get, you get z equal to 0. That is your origin. So this function has isolated singularity at origin, the point where the function is not defined, or the point where the function is not analytic is your singularity. Then third definition, principal part of Laurent's expansion for Fz. If Fz has a simple pole at z equal to Z0, remember I'm talking about simple pole for n equal to 1, right? At z equal to Z0, then we just now studied that limit z tends to Z0, z minus Z0 into Fz. Now here n is equal to 1 because we are talking about the simple pole. So the limit z tends to Z0, z minus Z0 into Fz is equal to a, and if this a, this limit is not equal to 0 or infinity, then the principal part of Laurent's expansion for Fz will be that limit a over z minus Z0. Let's do one example on this. For the function Fz is equal to z over z square plus 4, find the principal part of the Laurent's expansion valid in a deleted neighborhood of z equal to 2 iota. Now here Z0 is given to be 2 iota, right? So let's do this example. Now since limit z tends to Z0, which means z tends to 2 iota, z minus 2 iota into fz, that is your given function. So this is equal to limit z tends to 2 iota, because z naught is 2 iota, z minus 2 iota into fz. What is your function? Your function is z over z square plus 4. Then this is equal to limit z tends to 2 iota, z minus 2 iota, z over, the denominator can be written as in parts, z plus 2 iota, we fractionate this, z minus 2 iota. And this z minus 2 iota cancel over, which is equal to limit z tends to 2 iota, this is z over z plus 2 iota. Now put the limit over here, you will get 1 by 2, which is not equal to 0 or infinity. So we are having our capital A to be as 1 by 2. This is your capital A. So therefore, fz has simple pole at z equal to 2 iota. Thus the required principal part of Laurent's expansion for fz is equal to A over z minus z naught. What is A? This is 1 by 2. A over z minus z naught. That is z minus z naught is 2 iota. So this is your answer, right? Hence fz is equal to 1 over 2 z minus 2 iota plus gz. Yes, where gz is analytic at z equal to 2 iota. There is a very important remark. If f of z naught is equal to g of z naught and is going to be equal to 0, then their derivatives exist with g dash z naught not equal to 0, then limit z tends to z naught fz over gz is equal to limit z tends to z naught f dash z over g dash z, provided this ratio f dash z over g dash z is continuous at z naught, right? So this ratio must be continuous, then you get to have this, their limits to be equal, the ratio of their limits. Fourth definition, that is your residue, very important. If fz is analytic in a deleted neighborhood of z naught, then by Laurent's theorem we know that fz is equal to infinite sum, that is n going from minus infinity to infinity, a n z minus z naught the power n, where the coefficient a n is equal to 1 over 2 pi iota integration on c fz over z minus z naught the power n plus 1 dz. Right, this we know from the Laurent's theorem. In particular, for n equal to 1, just put n equal to 1 over here. You get a minus 1 is equal to 1 over 2 pi iota integration over c fz dz. Denominator will be 1 because power will be 0. So where c is any simple closed contour enclosing z naught and contained in the neighborhood, the coefficient a minus 1, this coefficient, very important, this is called the residue of fz at z naught. Right? Very important remark. If fz is equal to, that is, if it is equal to the form b over z minus z naught whole square plus c over z minus z naught plus d plus e into z minus z naught up to so on, then the residue of fz is equal to, at z naught, this equal to coefficient of 1 over z minus z naught. Now look at fz. What is the coefficient for 1 over z minus z naught? C, which is equal to c. So therefore 1 over 2 pi iota integration over fz dz. This is equal to c, right? Integration over c on fz dz equal to c, which is equal to residue of fz at z0. So this is another formula for the residue of fz at z0, just to check the coefficient of 1 over z minus z0 in your fz, right? So this completes this video. Next time we will be starting Cauchy residue theorem. Get ready for that. Do revise these concepts. These are very helpful in NET exams. So alright, bye, goodbye.